Hi, everyone. In this talk, we are going to talk about the new implementation of the elastoplastic material within the solid mechanics library of the finite element in Mathematica. In particular, we are going to start with a brief introduction of plasticity and how plasticity can be modeled, in particular, the computational approach to describe an elastoplastic material, and then we're going to go a little bit deeper into some detail for the implementation done within Mathematica. And then we're going also to observe how this framework can be applied to an application example. Let me start with a disclaimer. In particular, this code is still under development. So if you want to download this presentation, you cannot run it entirely. Some part of the code can still work because this is based on the actual implementation of the solid mechanics library, but some functionalities require the some function that are still under under development. So let's start with a brief introduction on plasticity. Plasticity is the ability of material in general to undergo permanent deformation. In particular, this is related to some sliding between atomic planes that can be observed as macroscopic changes of material properties. And in particular, we know from the initial study of Tresca from 1864 that we can divide material behavior from a structural point of view into two macroscopic classes, ductile and brittle material. And then, for a lot of time, we focus only on the first part of this curve, in particular, studying what is computationally known as linear elasticity. However, this is focusing only on the first part of the curve, while we may need to model also the remaining part of the curve, especially for ductile material, as for instance, the steel. To do that, we need, first of all, an approximation of this curve beyond the elastic limit. So we can try to continue with the linear elasticity, so to approximate the relation between stress and strain with a linear relation that is known as a hook law. But after the elastic limit, the solution obtained using this linear elasticity can represent a non-physical behavior. So we need another way to model this material. The simplest way is to use another straight segment. In particular, we can divide into two particular behaviors: a perfect plasticity that allows that the material is able to sustain whatever stresses we want. The stresses remain to the yielding stresses, while the strain can increase. Otherwise, we can see an hardening or a softening, so a change into the material elastic limit. To model this elastoplastic behavior, we need three main ingredients: a yielding criteria that tell us when, in terms of stress or strain, the material is beyond the elastic limit, and then we also need a flow rules that tell us how the plastic state evolve after the limits, and also an hardening model if you want to describe changes into the elastic limit. Yielding criteria generally can be expressed as a function that allows that give us a limit based on some measure of the stress. For instance, the von Mises yielding criteria tell us that the material is beyond the elastic limit when the von Mises stress is higher than the yielding stress. We can also notice that this function can represent a surface into the principal stress space, and the von Mises function, the von Mises yielding criteria represent this circle directed along the bisector of the plane while the transfer yielding criterion represents this hexagon. If we consider a plane stress case or a bidimensional spaces cutting this along with a plane normal to one of the main components, we can see that the circle is cutted along the diagonal direction, giving us this well-known figure. Then we need a flow rule. The flow rules basically tell us what happened to the material beyond the plastic limits to be able to come back into an acceptable state. So for instance, if we consider a particular state that is outside the plastic limit, this is the yielding function, we need a rule to put back the state at least to the boundary of this of the surface. And then in them, we may also need some hardening model that tell us how the elastic limit may change due to the variation of the material behavior. Since we are in small strain plasticity, we consider the strain decomposed by an additive decomposition. So the total strain is generally composed of an elastic part and a plastic part. And to describe plasticity, we need a flow rule that describes how the plastic variable changes over the step of the time. We can say over the time. In particular, this relation tells us that the increment of the plastic variable is proportional to the derivative of a plastic potential. In particular, this increment can be seen as a discretized variable with respect to the time. So 1 over the increment, and that multiply the differences between the variables and the values of the variable at the previous step. And this relation can be expressed also by considering the increment of this plastic multiplier, and this allows us to simplify the time, because in this case we can see this relation as talking about increment in terms of solving step and not in terms of time, because in this case since we are talking about linear elasticity, there is no dependence on the time. And so we can solve this equation with several iterations over the material. So to solve this problem, we can implement a predictor corrector algorithm that can be done as expressed in this scheme. We can, once we solve the equilibrium, we can use all the function from the mathematical solid mechanics PD library. We can evaluate the stress strain, and in particular, we can evaluate the yielding function. If we are beyond the yielding point, we can write this the previous set of equations that give us an evolution for the plastic variable, and then we can compute another step of we can compute a new solution of the elastic PDA, the elastic problem, accounting for the evolution of the plastic variable. So going into detail of this implementation, we can, as mentioned before, start from a solution of a classical elasticity problem. So the solution is given in terms of displacement and we can compute also elastic strain, total strain, and stresses. In particular, we can use the solid mechanics strain stresses and the Vovic stressing function to evaluate the current elastoplastic state. So given a particular set of boundary condition meshes, given material properties like the Young modulus, we can, and setting a yielding point, we can obtain a solution in terms of strain, displacement, strain, and stresses. In particular, by increasing the strain, there will be this point here. This point represents the yielding point of the material. So every solution computed in gray here beyond this point is a non-physical solution and need to be put back into the plastic state. To do that, we need to write the plastic flow equation, and in particular, this set of equations is a set of 8 equations with respect to 8 unknown, and then it may be solved easily. We need to solve this problem with respect to 6 variables for the plastic strain tensor, and then also the alpha multiplier and the plastic multiplier. In particular, we can start within the von Mises criterion that give us a yielding function like that. By deriving this yielding function with respect to the stress and to the back stress, we can obtain a relation like that. And it's important to notice that here the stress contains implicitly also the plastic variable, because general stress evaluation, the stress can be seen as a function of the elastic strain. In this case, we are considering both the elastic strain and plastic strain, so the stress is a function of the total strain minus the plastic strain. In particular, this is the relation of the solid mechanic stress for a linear elastic material with respect to the general strain. But for an elastoplastic problem, the strain is decomposed into an elastic contribution and a plastic contribution, so the stress is computed effectively only to the elastic contribution, giving us a relation to the strain with a tensor expressed like that, of a symmetric tensor of 9 components. From this tensor, we can extract this set of equations, 6 equations from the first row and the other 2 equations. In particular, by extracting this equation, we can observe a relatively complex system of equations like that. Let's, for instance, put some numbers inside this equation, like the Young modulus of the material, the yielding point, an hardening modulus, and some initial values for the plastic variables. And then the system is a little bit simplified, and this system of equation can be solved with respect to the plastic variables, for instance, using find root, obtaining a solution for the plastic variables. This solution can be used as a plastic strain, so an additive strain to the material, and then compute once again the solution using the solid mechanics PD component and the solve of Mathematica. Let's go into detail by analyzing a practical example. This is a simple square rectangular domain with a sliding boundary condition on the left bottom side, while the right side is pulled to the right. As mentioned before, we need to analyze this 3 plus 1 iterative step. So we start by defining mesh, variable, and of course the material parameter, and then the boundary condition. As mentioned before, an imposed displacement on the right side, and also a sliding condition to the left bottom side. Then we can use and solve and the solid mechanics PD components in particular. The solid mechanics PD component give us the PD's set of equation of an elastic boundary value problem, and then the solved values give us the solution in terms of displacement. Once we obtain this displacement, we can of course visualize the displacement in gray the undeformed mesh, and in blue the deformed mesh, obtained from with a simple elastic solution. But we need another step. We need to evaluate the stress, strain, and stresses. In particular, since we are using the von Mises yielding criterion, we can use the von Mises stresses. By observing the von Mises stresses, that we can understand that for a problem like that, this is a constant, but we need also to understand if this is an acceptable value or is beyond the elastic limit. And in particular, This point in blue here is beyond the elastic limit because it's higher than the yielding stress. So we need to account also for the evolution of the plastic variable. To do that, we can write the plastic flow equation as we've seen before, but I will come back to this in a moment. And then we can iteratively solve the solution. In particular, we can use a function to solve the plastic problem and then compute once again the solution using an solve. And this gives us a set of solutions, give us a new displacement that now account also for the evolution of the plastic variables. So by evaluating the new displacement, we can first of all observe that the mesh is a little bit show a different displacement. In particular, the right side remains the same because this is imposed by the boundary condition, but we can see an higher contraction on the top side. And if we try to evaluate the new von Mises stresses, in this case, we can see that the von Mises stresses is pulled back to the plastic limits of the perfect plasticity. Okay, some notes of the implementation. Since we need to write this set of equations, we need to understand where is the point, where is the optimal point to evaluate this solution. In particular, we are talking about FEM, and we know that for an FEM analysis, we know the solution only on a particular point. In particular, we know the displacement in terms of displacement of the nodes of the mesh, while inside the element, we approximated this solution with special shape function. Let's take a bidimensional mesh like that, composed of four square. We know that the solution can be approximated using particular shape function like that. And write the solution as a composition of this shape function and the nodal values of the displacement. So we discretize our space of solution into a small segment, and for each of this segment, we describe the solution with special shape function. Moreover, we also need to integrate this function, and for that we generally use a Gauss rule. So the integration is obtained by weighting the values of the function computed on the Gauss point by some special weights obtained by the Gaussian rule of integration. What does it mean for us? This means that we discretize the displacement, but its derivative, which for instance can be seen as the strain, but also the stresses, because we have a linear relation between strain and stresses, it's approximated with a lower degrees of approximation. In particular, if we consider a linear approximation of the displacement, its derivative is approximated with a pairwise constant function. This means that while for the displacement we know the exact solution on the nodes, and inside the element we approximated the solution, for its derivatives, this isn't true anymore. In particular, by taking the nodal position in black here, we know only an approximated solution. However, there exist some special points named as superconvergence points that represent some points in the space where the derivative of the main unknown is approximated with a higher degrees than expected. In particular, can also be demonstrated that for polynomial functions that are generally used for the FEM implementation, these points correspond to the Gauss point of integration. This is the reason why the plastics flow equation are solved over the Gauss point for each mesh. This means also that when we talk about evaluation of the yielding function function, we need to evaluate this function for each of the ghost point of the meshes, and then we need to solve the plastic flow equation for each of these ghost points. For this reason, we want a faster way to work with this set of equations, and so inside this equation that record a plastic solution, we can use some compiled function. In particular, we can write a compiled Newton-Raphson that iteratively solve the subset of equation, where here we use linear solve to solve the set of equation, but this function is exactly the system of equation that we have seen before with respect to the plastic variable. In fact, this can be obtained by replacing the symbolic variable of the previous example with the argument of this new compiled function. And this is the same set of equations seen before. And another advantage of this compiled function is that they can be applied they can be parallelized over the integration point, and we can solve this with a single comma that is optimized for this type of solution. Okay, let's go into a final example that shows us how this can be useful. Let's, for instance, take the Cook's membrane, which is a commonly used benchmark for this for the solid mechanics application example. Let's take this mesh and let's give us some triangular elements. So we can specify the boundary value problem. In particular, the left side is fixed here, and we can apply a vertical force to the right side. And then we can assign some material properties and solve the problem. As seen before, we obtain an elastic solution, but we also need to understand if this is a physical or not solution. To do that, we need to evaluate its stress, strain, the von Mises stresses. In particular, we need to compare these von Mises stresses with respect to the yielding point. Red region here represents the element beyond the elastic limit, and for this element, we need to solve the plastic flow set of equation. As mentioned before, we need to solve this iteratively. In particular, we can stop when the increment of the plastic variable is below a certain tolerance. Then we will obtain some updated displacement that now account also for the plasticity, elastoplastic behavior. And in fact, we can see that the red deformation here shows the elastoplastic behavior that is a little bit different due to the plastic deformation that we can observe. And we can observe how this plastic deformation affect only the region and that only the elements that are beyond the yielding point. So, this is what we are currently working on. We are mostly work on finding the optimal way to integrate this iterative solution of within the solid mechanics PD library of Mathematica. But we are still working. But we are also working and thinking about future integration, like integrating with several yielding criterion, or also implementing a different model of hardening, not only a linear hardening, but also like a kinematic hardening, and allowing the user to insert a custom hardening law. Okay, so thank you for the attention, and I would be happy to answer any question for the audience. Thank you. Yes, I will update the notebook as soon as possible, and yes, We are working also to implement several different criterion. So yes, also the more common yet criterion. I'm not able now to talk about when this will be available, but we are working to implement different criteria. Yes.